Graphical Analysis. Graphical Analysis. We have an external horizontal force, F, is applied to a 4.6 kilogram toy car initially at rest, and it moves in a straight line. The force varies with the car's displacement, as shown. How much work is done by the applied force as the car moves the first 10 meters? Determine the kinetic energy of the car at the 10-meter point. What is the velocity of the car at the 10-meter point? Then, what is the total work done by the force in moving the car to the 30-meter point, which is over here? Then, what is the velocity of the car when at the 30-meter point? Okay, before we start answering that, let's have another question. Why can't we just use the work equation to solve for work algebraically, which is work is F times displacement? Why are we using a graph for the problem? Well, the work equation is only valid when we're finding the work done to a constant or an average force. The force in this problem continually varies, so we need to add up the force times each distance for every single little distance. Now, we're not going to do that. We have a simpler way. In calculus, you do it with integration, but for this, we can just have our graph, and we'll use math by taking areas. We're doing geometry here. We're going to plot the force versus a displacement, and actually it's already been plotted, and you take the area under the curve. That tells you the work done. So we want to find the work done by the applied force for the first 10 meters. That goes from here, from 0 to 10. And what we do is we draw this line here, and I'll erase that because it's not really straight. Here's our curve. Now you may think it's funny that I'm calling that straight line a curve, but you're allowed to do that. And straight line is just a special case of a curve. So let me erase that. I don't think that was terribly helpful. So we're going to take the area under that triangle from 0 to 10 meters. So the work done is the triangular area under the force versus distance curve from x equals 0 to x equals 10. That's a formal way of saying what I just talked about. The height of the triangle, and where did this purple line come in? Well, I wanted to find how high this was. So I drew a horizontal line parallel to the axis, the x-axis, and I got 20. So the height of the triangle is 20 newtons. Now I want to find the area. Area of a triangle, which is the work is equal to the area of the triangle, which is 1/2 times base times height. And we have work is 1/2 times 10 meters. That's how far we've gone in 10 meters. And the height is 20 newtons, which is a Newton meter. And what's a Newton meter? Joule. So what do we have here? 100 joules is the net work done from 0 to 10 meters. Next, find the kinetic energy of the car at the 10-meter point. Use one of our favorite equations here, work energy equation. Initial energy plus work is final energy. The initial energy is 0. The car is at rest, and we're not going up or down any inclines. And we want to find E final at 10 meters. The work done on the car was found in part A, and that's 100 joules. So look, we have 100 joules here is equal to final energy. The final energy is all kinetic energy. We didn't talk about the car changing height at all, so we'll assume it's at the same height the whole time. So the initial energy plus work is E final. The work, because the initial energy is 0, is just kinetic energy, so the kinetic energy equals the work. So it's 100 joules. What's the velocity of the car at the 10-meter point? Well, what did we find on the previous slide? The kinetic energy, which is 100 joules. So we can use that to find the velocity. Kinetic energy, 1/2 mv squared. We'd like to find the velocity, so we just switch the order, and we have 1/2 mv squared as ke. Multiply both sides by 2, and we get mv squared as 2ke. Divide through by m, and we have v squared is the square root of 2ke. Then just take the square root of both sides, and here's our answer. Once again, 95% of the problem gets you there. And then finally, you put in our variables here, and you get a velocity of 6.59 meters per second at 10 meters. What's the total work done by the force in moving the car to the 30-meter point? So that establishes our base, and we need the area under the curve. So the curve, even though it's straight line, goes up and comes down. So what do we have? We have another triangle. So the work will be the area of that triangle, which is 1/2 times the base. The base is 30 meters. The height once again, is 20 newtons, and we get 300 joules. What is the velocity of the car when at the 30-meter point? As before, the work done is equal to the final kinetic energy. Once again, use the kinetic energy equation to find the velocity. We showed the complete algebra back in Part C. We took some shortcuts here just to save some room. So our work is equal to KE, which is equal to 1/2 mv squared. And let's see if we can just do this in our head maybe. We want v squared all by itself. So if we multiply both sides by 2 over m, right, that'll cancel this out. And then we'll have 2 over m in front of the KE, just like we have here. And then we'll switch the sides around, so we have v squared on the left. And then you just take the square root. So v is equal to the square root of 2 over m times the kinetic energy. Put in our values, and we get the velocity is 11.4 meters per second. And that's faster than the previous problem where we were just going to 10 meters. And that's good because we have this force being applied. It should be accelerating it the whole time. And it does.